we'll do some special cases of algebraic extensions. So let us assume that E is an extension of f and alpha comma beta be algebraic over f. And also we assume that the degree of f of alpha is equal to n and the degree of beta f is equal to n for some integers m and n and m. Our objective is to find out f of alpha comma alpha beta. This is actually nothing but f of alpha beta and is generated by elements from alpha j, alpha I, alpha beta j, 0 less than or equal to I less than n, 0 less than or equal to j less than maximum of m and n. So this is actually can be written as elements from alpha I, beta j, alpha I, beta j, I 0 less than or equal to I less than n, j less than 0 less than or equal to j less than m. Because depending on which is greater, these elements will vanish after m or n. So alpha cannot go beyond n minus 1. Beta cannot go beyond m minus 1. So if we group together, the elements are of this form. And this is actually nothing but, so alpha, f of alpha from alpha beta is nothing but, this is actually nothing but f of alpha beta. That is the definition of alpha beta. So what I'm trying to say here is if there are more than one element, common element, if there is a common element in this extension, then we can take out all but one or use only one of them, use only once. So in other words, if you have more than two elements like alpha, alpha beta, comma alpha gamma, then it is going to be f of alpha beta gamma, where gamma is also algebraic. Let E is an extension of f and alpha beta be algebraic over f, and we are going to assume that beta does not belong to f of alpha and alpha does not belong to f of beta. Both are outside each other. And we are going to assume that degree of alpha over f is equal to n and degree of beta f is equal to m. is to find out degree of the degree of f of alpha comma beta colon f of beta, and of course f of alpha comma beta colon f of alpha. This is actually equal to f of alpha beta colon, you can write it like this because this is an extension of beta over, simple extension of beta over f of alpha. Or let me write this as an alpha here. That is more easier, and we'll come back here again as beta here. So this is actually, this means what? This is actually equal to the degree of the irreducible polynomial of beta over f of alpha. This is our, these two are same. So when you take the f of alpha comma f of alpha beta comma column f of alpha, then this is our common base field f, and beta is just outside that. So that is what I am saying here. It's irreducible, degree of irreducible polynomial of beta over f of alpha. Beta is actually outside f of alpha and alpha is outside f of beta. So this actually means that it is actually a degree of irreducible polynomial of beta over f only, because the irreducible polynomial of beta does not contain any coefficients from f of alpha minus f, because beta is outside f of alpha. And what is this? This is nothing but So f of alpha comma beta, the degree of f of alpha comma beta over f of alpha is same as the degree of f of beta over f. Similarly here, this will be f of, this is the degree of f of alpha comma f. We'll use this result in one problem. Find the degree of q of root 2 comma root 6 plus root 10 over q of root 3 plus root 5. we are going to combine all these results to find this row. So what is this? Q of root 2 comma root 6 plus root 10 is equal to Q of root 2 comma root 2 times root 3 plus root 5, because I am going to take root 2 outside. And this is actually same as Q of root 2 comma root 3 plus root 5. Because this is a common factor and we know that we can get rid of one of them. And root 3 plus root 5 does not belong to Q of root 2, and root 2 does not belong to Q of root 3 plus root 5, because you cannot express root 2 cannot be root 3 plus root 5 cannot be expressed as a linear combination of root 2, and root 2 cannot be expressed as a linear combination of root 3 plus root 5. So this implies Q of root 2 comma this implies the degree of Q of root 2 comma root 3 plus root 5 over Q of root 3 plus root 5 is equal to Q of root 2 comma Q. Just like this. This is our root 2. This is our root 3 plus root 5. And all these conditions are satisfied. And this is nothing but so this is actually Q of root 2 comma root 3 plus root 5, but that is same as this. So this implies Q of root 2 comma root 6 plus root 5 colon Q of root 3 plus root 5 is equal to . Now let us assume that we have an extension here. E is an extension of F. E doesn't need to be algebraic, but just an extension, and alpha 1 dash dash alpha n be in E be algebraic over F. To avoid the trivial situation, what we are going to do is alpha I does not belongs to F of alpha j when j is different from I. Just to avoid this trivial situation, I am not going to assume that one of them is inside the simple extension of another one. So alpha 1 is algebraic, so we can write it as f of alpha 1 is an extension of f. It's a finite extension of f, because that is the definition of the simple extension. So simple extension is the smallest extension containing alpha 1, and if alpha 1 is an algebraic, though it is going to be finite. This is actually going to be a finite extension of this is also a subfield of alpha 1 comma alpha 2. Like this, f of alpha 1 comma alpha 2 dash dash alpha n. The meaning of this one is the smallest field containing alpha 1, alpha 2 dash dash alpha n and f. So this is a finite extension. This is a finite extension. What does that mean? If this is a finite extension of this and this is a finite extension of this, then that means f of alpha 1 comma alpha 2 is a finite extension of f. And that implies f of alpha 1 comma alpha 2 dash alpha 3 is a finite extension of f, because this is going to be a finite extension of f of alpha 1 and alpha 2, which is a finite extension of f, so this is true. So we have f of alpha 1 dash dash alpha n is a finite extension of f. So if alpha 1, alpha 2, etc., alpha n are algebraic, then f of alpha 1 comma alpha 2 comma alpha 3 dash dash alpha n is a finite extension of f. Now let us assume that let E be an algebraic extension of finite dimension of, or you can say let E be a finite algebraic extension of f. What does that mean? That means that E comma equal f is equal to n for some integer n. Now what happens is, then let alpha 1 belongs to E minus f. This means alpha 1 is algebraic because E is algebraic, and that means f alpha 1 comma f is finite, or f is f of alpha 1 is an extension of f of alpha. Now take alpha 2 belongs to f of alpha 2 minus f of alpha minus f. Sorry. Take alpha 2 from E minus f of alpha 1. This is E, this is f, there is an alpha 1 here, this is our f of alpha 1. We are taking another element outside f of alpha 1, alpha 2 here. Then we have f is a subfield of f of alpha 1, which is a subfield of f of alpha 1 comma alpha 2. So of alpha 1 comma alpha 2 is a field containing alpha 1 and alpha 2 and F. We'll take another element here, alpha 3. Continue this process until we arrive at f of alpha 1 comma f of alpha 2 comma f of alpha 1 is equal to E. This is possible because E is a finite extension of F. You cannot go infinitely. If you take here, then you can take a 4 here, but it will stop. The process will stop for some n. And once it stops, then there is no more elements from E which is not in here, because E is a finite extension. So what does that mean? That means if E is a finite algebraic extension, let us use this word finite. If it's a finite algebraic extension of F, then E can express as the extension of F over a finite number of fields. So what does that mean here? If E is a finite algebraic extension, then there exists alpha 1 dash dash alpha n such that E is equal to f of alpha 1 comma dash dash alpha n for some n. Now we'll assume that see here what I'm assuming is E is an finite algebraic extension. If it's a finite algebraic extension, we can express E as an extension of alpha 1, alpha 2, alpha n over F for some n. But what happens, let's say we are assuming that E is algebraic over F, and E is equal to f of alpha 1 dash dash alpha n for some alpha 1 dash dash alpha n in E. Then definitely E is a finite extension, because we know in the previous result that if you can express any field like this, then it's a finite extension. So the final result is let E be an algebraic extension of F, then E is a finite extension of F if and only if there exists alpha 1 to alpha n in E such that E is equal to f of alpha 1 dash dash alpha n for some integer n. Let us do a problem. Let E be a finite extension of f with degree is equal to p for some prime p, and that is E over f is equal to p. Since alpha E is a finite extension of f, E is a finite extension of f implies E is an algebraic extension of f. So let alpha belongs to E minus f, outside f, inside E, implies alpha is algebraic over f. So that means E is an extension of f alpha, which is an extension of f, and that implies the degree of E over f is equal to the degree of E over f of alpha times f of alpha over f. This is p and this is a number greater than 1. Why? Because alpha does not belong to f, it's outside f. So this has to be p because it's a prime number. It's a product of two numbers of which one of them is greater than 1. So that means f of alpha colon f is equal to p implies E colon f of alpha is equal to 1. So this is 1, this is p, and this is p. When you have a degree of two fields equal to 1, they are actually same. This implies E is equal to f of alpha, which implies E is a simple extension. So if E is a finite extension of degree prime number, then it has to be a simple extension.